Hello and welcome to another episode of the Oxford Online Maths Club. My name is James and today I'm joined by Flora.
Hi, I'm Flora. I'm a third year maths student at Mansfield College, Oxford.
And we're also joined by you. If you're watching live, hello to the people who are joining us in chat. I can see Alfie and Rafael and Darishle and Halikar. Chat is hosted over at slido.com. If you head over there, you can put in, I guess, your name or a mathematician's name or whatever you like. Somebody's recognised Flora. Somebody in chat who is anonymous. That's the other thing. You can also be anonymous. Someone in chat who's anonymous just says Flora in all capital letters.
It is indeed Flora.
Ramanajan's here. Shout out to you, another anonymous person who says hello, and Molly's here too. Good to see you. Good to have you with us. I guess some people have recognised Flora because this is the third time you've been on the show. I think.
Yeah. It was like once per season, basically.
Once per season. That's how often we have Flora on the live stream so far. And you've been moderating chat a few times as well. Speaking of which, moderating chat today, I think we've got Christian and Charlie in the house. So goodness knows. Hi, Christian and Charlie. Hello, Rilo as well. And an anonymous person shouts hi. Ali's here, says bonjour. Right, cool, okay. That's the welcomes. I wonder whether they want to see, sometimes they do a how's your day poll. I wonder if they wanted one of those, because we haven't done one of those in ages, so I'm going to slightly hijack the start of your talk to do a how's your day poll, which is on Slido, and it's on the bottom of the screen, but it's a bit hard to see on the bottom of the screen. Well, there you go, 100% has just shot up on 4 stars. This is a feature I discovered on Slido, that you can do star ratings on things. I think the application is supposed to be, how do you like my maths content or something? But
feedback.
Feedback, like actual feedback on, I don't know, strategy business meetings or something.
How was your day is a valid poll. I like it.
Valid 5-star thing. Let us know in the Slido chat, by the way, if we're either too loud or too quiet or completely different volumes from each other. People in chat at the moment are saying, not so good, they've got COVID, says an anonymous person. Sorry if you've got COVID, sorry if you're isolating. If you want something to do during isolation, we have about 30 back episodes of Oxford Online Maths Club for other topics.
That would keep you entertained.
Keep you entertained, including Penrose tiling, which was with Flora in before, which somebody's mentioned. We haven't done the poll since the Matt live stream, which was back in the days when we had some Matt questions on, and it felt important to check how people were doing in the run-up to Matt. At the moment, the average is 3.7 overall, which is, I think...
That's not bad.
By our standards, that's quite... just ticked up to 3.8 on average as we went through there. I can just quickly, I think, if I switch to... No, I can't. I can't get more of the graph on screen. It's at about 43% 4-star. As always, I'm watching out for people who vote 1-star or 2-star. If your day is 1-star or 2-star today, then hopefully we can get that up to 1 more star. Right, okay. What an enthusiastic start. The kind of live attitude that you get. Brilliant. Figure skating, says Darishle in chat. Yeah, okay. If you're watching the replay, this live stream happened during the Winter Olympics. It's on the day at which Great Britain have maybe got locked to at least win 1 medal. We'll see on the future replays whether that's how many medals Britain end up with in total or not. Audio's alright. 5 stars because Flora. Right, okay. I told Flora that Flora's fan club would be in. So that's nice.
Well, I hope you like it.
I think I should hand over to Flora to tell us about measure theory. Over to you.
So, I've got a few kind of interesting diagrams to whet your appetite, but I'll start with, what is measure theory? Measure theory is an area of pure maths which tries to rigorously measure things. So all your life, probably, you've been measuring things. If you think about a ruler and measuring the length of something, that's the most basic example I could think of. Or like measuring area or volume. Like you're always measuring, different things in life. But measure theory is the kind of abstract version of that. So we look at like, how abstract can we make it? And pure maths is like, we're going to set up this framework for how we measure things that then can be applied to lots of specific examples. Which kind of leads me on to, well, are we going to measure any things, or are we going to measure specific types of things? And it is going to turn out to be the second one. We're not going to be measuring just about anything, but I'll introduce a kind of like framework of what a measure space is, which is like the way you build up a kind of proper mathematical framework of measuring things. But then we will do some actual examples to help you kind of get your head around it. So first we're going to start with some kind of facts about area, because area is like probably the easiest way to kind of visualize measuring things. It's the way that you might have come across at school or in life in general. So the first thing I'm going to mention is complements. And now you might be thinking, what does complement mean? This links to set theory in a way, and measure theory does link to set theory quite a lot, so that will be a theme kind of throughout today. So if you don't know what complement is, I'll explain it in steps. So basically, we have this rectangle, and then what's inside this rectangle is like some set. It's a set of points. The points are inside the rectangle. And this thing over here, I've got to get my laser pointer out. This thing over here, that you might, hopefully you've seen that symbol before, it doesn't matter if not. It's a Greek letter, it's called omega, but basically what I'm saying is my set is called omega, and that is quite a standard thing in set theory, in measure theory. So that all the points inside the rectangle is my set omega. If we have like a subset, which is called A, so all the points inside this circle, then the complement of A is all the points that are not inside the circle. So it's omega without A. So the points that are not included by A. Hopefully that made sense. So when we think about area, it's just kind of a general fact that you might have thought about, you might not have thought about, that if we have the area of this rectangle, and then if you have the area of A, you may or may not know how to find the area of a circle. But if I told you the area of A and the area of the rectangle, and then I asked you, okay, what is the area of a complement, this weird kind of shape with a hole in it? Hopefully you'll be able to say, well, it's going to be the area of omega minus the area of A, because obviously the area of this bit and the area of the surrounding bit have to add up to the area of the rectangle. And that might seem pretty obvious to begin with, but I'm just emphasizing it because it's kind of an important point for later on about like how we can measure things and what we can measure. Cool. Oh, and the next thing that I'll briefly mention is unions. So if you have two things, like two subsets, so you've got A and we've got B, and these are not overlapping, then if I told you what the area of A was and what the area of B was, then you'd be able to hopefully tell me the area of A union B. A union B means all the points of A as well as all the points of B. So the area of A union B would be the area of A plus the area of B in this context. And I'm going to leave it there for now, but we'll see this again later on. Okay, so now, quick kind of change of direction. We've talked about area. Now we're going to think about sets, and then we're going to kind of bring it all together in what a measure space actually is. So I'm going to define something, which is, I think, really cool. I think set theory is really cool. What I'm defining here is called the power set, and that is the set of all subsets of X, or whatever set you have. So X is a set, it's some collection of things that we call elements, and then the power set consists of all the subsets. And now, quick refresher, what is a subset? A subset is another set, so another collection of things, which is contained like within the bigger set X. So I'm going to do an example which might make it a bit clearer. So if X is a set with three elements, the elements are A, B, and C. They could represent numbers, they could represent shapes, or even other sets. Basically, they're just three things. We don't know what they are, A, B, and C. And so then we need to think about, okay, what are the subsets of X? Anyone may give ideas at this point.
Go on, chat. Okay, chat can tell us some subsets of things. I suppose, is your subset made up of some of the things that are inside the overall set? That's what a subset is, right?
Yes, that's generally what a subset is.
Okay, so, and then your power set is like the set of
all of those things.
Sets. Okay.
Yeah.
So it's a set of sets.
It is a set of sets, and you see that a lot in set theory. If you do study set theory at university, it's literally like sets of sets of sets. There's just lots of sets, lots of curly brackets.
We thought about doing today's session just about set theory, to just have more and more curly brackets and empty sets and things. Speaking of, Darishley in chat and also Ali have mentioned the idea, and here comes some more people. People are typing. Rilo as well has got the idea. These people have each suggested several subsets, but one of them that they've suggested is the empty set, the one with no elements in. Does that count?
Oh, wow. It does count. So people have already kind of gone for it. I was going to start with the kind of simplest ones, which are, okay, we can take each element, have the set that just contains A, the set that just contains B, the set that just contains C. So like, if the curly brackets are overwhelming, just think of this as the set that only has A in it. And then obviously we could take two elements and that would still be a subset. So you'd have AB, BC, A and C, or you'd have A and B and C. Hopefully everyone knows that like the actual set is also a subset of itself, because of course it is contained within itself, because it is itself. And then, like someone said, we have the empty set. And so it's a bit weird to think about how the empty set is a subset of X. The empty set is actually a subset of every set. I think it's a really fun area of maths because you can make really silly statements. So the empty set is the set which has no elements. That's the way it's defined. Like, it is empty. That's it. Like, it doesn't have anything in it. So you can say statements about elements of the empty set. Like, every element of the empty set is in X. Well, that's true because there are no elements. It's what we call vacuously true. You can say any statement about the elements of the empty set because there are none. So it's true. It doesn't matter, you know?
It's sort of like your way of checking whether it's an empty set is to check whether everything in the potential subset is in the big set. And that's true for the overall set. I felt like maybe that was a technicality, but I guess it matches the definition there. Everything in the set is in the set. And it was also true for the empty set. Everything in the empty
set. Yeah, so all of these elements are in X, and then all the elements of the empty set are in X, because it doesn't have any. All the elements of the empty set are elephants. All the elements of the empty set are pink. You can literally say what you want about the elements of the empty set.
It's a sort of fun logic thing, I suppose, that you can start all of the elements in the empty set are, and then say just about anything, right?
Yeah, literally. And I think that's one of the really fun kind of logical set theory statements. But yeah, it is a good one.
And somebody's noticed.
So hopefully,
I've just turned off chat on the screen so that we could see the empty set symbol. I'm going to turn it back on now.
Oh, it was covered up. Sorry.
Also, somebody's noticed that you write really fast. How are you doing that? Did you?
Oh, that was not me writing. I wrote this before. Yeah, so this is just the magic of PowerPoint. I can write the empty set symbol up here as well, so people can see it. It's just a 0 with a line through. Yeah, this was not me writing. That red empty set, that was me writing just now. But in general, most of the things on my slides I have drawn or written beforehand, and then I'm just using PowerPoint transitions to make them appear. This is because I don't trust myself to write fast enough and neat enough live.
Someone in chat says there are 8 things in the power set. So the power set here, this is all of the things, all of the different subsets. There are 8 things, and somebody else said something about binary choices of like picking things or not picking things.
Very interesting. I was gonna say something we could put in further reading is thinking about how many elements there are in the power set of a set. Because here, you're quite right, we have 3 elements in X, and we have 8 elements in the power set, and you're thinking, what links 3 and 8?
I think people in chat are getting there.
Yeah, you might think of it straight away, or that might be something to kind of look up later on. But
it's one of those times I wish that I didn't have chat on the screen, so that there's some air of mystery. Chat's doing it. Okay, this is the alternate reality where we talk about set theory for an hour. I should let you move on from the power set.
So that was the little set theory side. I will move on to the proper measure theory content now. It was kind of necessary to understand some set stuff because they are quite linked. But yeah, so I'm going to talk about a measurable space. And so it's something that we're going to kind of build up. And eventually we're going to build a measure space, but we're going to start with like measurable space. So like, what can we measure? How are we going to build that? And so I've kind of got a list of ingredients. So first we start with one set. Now I'm calling it omega. That's quite a standard thing. My rectangle on the right is just a way of visualizing it. Not every set is a rectangle. Disclaimer. But if it helps you kind of think of the set as like some area, then that's okay. We're also going to have the power set, and the notation for the power set is P of omega, like we saw in the previous slide. So I've drawn here just some like shapes which are subsets of the rectangle, like bits of the area, just to kind of help you visualize subsets in a way. So the power set contains all possible subsets of omega, including omega itself and the empty set, don't forget. So we've built up a measurable space. We've got a set and we've got all these subsets that we're going to be able to measure. Like the power set consists of the things that we can measure. So let's actually measure them. So the way we're going to do that is with something called a measure function, very imaginatively named. And this is basically going to be something which measures our sets. So we're going to take a function. It's going to be called M for measure, and I've written it as M of A, like the way people often write a function as F or F of X or whatever. I've put A to kind of emphasize that we're going to be measuring sets. So it's a function from the power set. Now, so the power set is like what we put into the function. That's the domain of the function, if you like. I challenge you, chat, what does the function go to? What's the output? What are you going to get out when you measure a set? Thinking about the fact that area is a measure, length is a measure, volume is a measure, that kind of thing. What do you think our output will be?
Okay, so you want a sensible sort of place for the outputs to live. Mm-hmm. Inputs, I give you a power set, your measure function. In return, it gives me trade deal. I give you a second power set.
I give you subsets. You give me.
I receive. Alfie says some scalar. So scalars are real numbers, right?
Yeah.
Yeah. That's
scalar,
a good start.
Yeah. So it's a scalar. It's not going to be a vector. Good one.
Good idea. Yeah. A scalar. I'm glad that no one said complex number yet.
Yeah. Please don't say complex numbers. It's not going to be a complex number.
And there's some sort of range. There could be some range of these. Says Rilo. So maybe there's some acceptable range. An anonymous person says maybe they have to be positive. Because I think you learned in school that area has to be positive, right? So maybe that's linked to the idea that
you can't have negative area. So we're getting onto the idea. So I'll do a bit of a reveal. It's the non-negative real numbers. And when I say non-negative, some people say positive when they mean this. What non-negative means is all of the positive numbers, but also zero. Because when you measure the area, or like you do the measure function of something, you need to be able to say, well, this has measure zero. This has zero area. If it's just a point, that doesn't have any area. So if we measured it, we would get zero. And then obviously we can have any real number, any positive one, I mean, any positive real number, because we're going to be measuring like the size or like the area or the something. So I've drawn previously, not right now, I've drawn this little kind of diagram to visualize it. And this is just kind of mess to show that we've got like all these messy subsets. This is the whole power set. It has all the different subsets. We don't know what they look like. And then M is the function which takes some subset and it gives you a point on this line. So this is the positive real line, which includes zero and has all the positive real numbers. Okay, so that's the truth about a measure function, but it also has to have certain properties. So this is kind of the main property that it has to have. So here we're going to kind of look at our subsets again. I'm going to say, okay, if I told you what the measure of A, this subset, was, and the measure of B was, then what do we think the measure of A union B would be? So bearing in mind that like A and B are two separate things, you know the measure of this, you know the measure of that. What's the measure of the union, all the points of A and like as well all the points of B?
Okay, so what's our intuition here? For the measure is a bit like area, and we've got a set A and we've got a subset A and a subset B. People in chat, I'm going to give them a moment. People in chat are having a go at what they think. It's sort of a guessing game again, isn't it? For what they think the measure of this union should be, with measure being a bit like area.
Yes.
And anonymous people, and also Jerusalem, who I guess also counts as anonymous, really.
Unless it actually is.
Either A plus B, which I'm a bit nervous about because A on its own is a subset and B on its own is a subset. I don't know how to add subsets. But some people are saying M of A plus M of B. Measure of A plus measure of B, which I'm more comfortable with, right?
You're onto it. So the people that said A plus B, they probably meant to say like the area of A plus the area of B. It can get confusing with lots of letters knocking around, but so what you want to say is you're adding the measure of A and the measure of B together to get the measure of A union B, and that's good. That's right. So now I'm going to kind of like crank it up a notch. What if A and B overlap like this? So the points where my like little red dot is, these points, they are in both A and B at the same time. There is an overlap. Points that are in A and B. And now I'm going to say, okay, is this still true? I've put a big orange question mark here. Is this still true?
I
know
so now people are refining
my
guesses. Actually, while you're doing the question, some people in chat may be unhappy with the M of A plus M of B answer. Or I think asking about how subsets behave. Subsets can do this, right? Subsets don't have to be distinct.
Yes, they don't have to be. No, I was just kind of I was being sneaky with you. So subsets don't have to be distinct. If you think back to our example before, where we had I'm trying to get the pen. We had like A, B, C, and subsets of that were like A, B, B, C. Sorry about the messiness of my curly brackets, but you see here, B is in both that subset and in that subset. So you know that they can have points which are in more than one subset.
So current suggestions are that we should... Wow, so actually there's an argument in chat that I quite like, that people are thinking about what if A equals B? What if they're the same subset? Because then it's kind of uncontroversial that those subsets overlap. Unless they're both the empty set.
Yeah, exactly. If we had A equals B, then that's kind of another more specific question. What would the measure of A union be then?
And there's some suggestions from people like Theo and Molly, and I think Rilo said this at one point, and SV, that we should do M of A plus M of B, but then subtract, because we overcounted, subtract the measure of A intersection B, the overlap region. We take away the extra.
Yeah, section. Wonderful. So I will let that appear now. Oh no, it's going to be blocked by chat. This says measure of A and B. Yeah.
Chat will be back in a moment.
So yeah, chat will be back soon. So that's a measure of A and B. So if you think about, like James kind of already mentioned this, but if you take the measure of A and you add the measure of B, then what you've done is you've kind of counted all these points in the intersection twice. So if you just take away one of those, then you've only counted them once. So it's like you did all these points, all those points, and then all these points, but you like took away the intersection, so you didn't count it again. So that's what the measure of A union B is in general.
Is that like an axiom about how measure functions should behave?
Yes.
Okay.
Yeah, this is a rule, and all measure functions do have to behave that way. And it's so important that I'm going to put a yellow box around it. And now I'm going to invite people to think, okay, this rule that I've put in the yellow box, is there anywhere that you've seen anything similar to this before? Does it ring a bell? Does it kind of remind you of something? If you've done some kind of A-level maths, then it might remind you of something you've seen before.
Let's give chat a mo. I love this. Who is the sort of fastest finger? But people are going for similar things. Shout out to SV with the inclusion exclusion principle, but I'm going to Amelia and Ali and Nick is here and Raphael. Maybe some sort of link between this and probability.
Yeah. Yeah. I don't know if you meant to bring chat back, by the way.
Yeah. Sorry. Oh.
Yes. So you're absolutely right. And now we can move on to the next slide. So beneath, I have written the kind of equivalent statement, but in terms of probability. And so you're thinking, okay, this is basically exactly the same thing. It's just you've got a fancy P or you've got an M. And this fancy P, just as a refresher, means the probability of A union B, where A and B are some things that could happen, may or may not happen. So, okay, what does this have to do with probability? Well, it turns out, everyone, that this is kind of plot twist. Probability spaces are a type of measure spaces. Whenever you have been doing probability, if you've been using any rule like this, where you kind of add together probabilities, take away the intersection, you have, without knowing it, you've been using kind of the theory of measure spaces already. It's just a specific case of a measure function. So here we go. The set omega is the sample space. And you may have heard that terminology when studying probability. Sample space is like all the possible outcomes that you could get. So like if you roll a dice, your sample space consists of 1, 2, 3, 4, 5, 6. Assuming it was a d6, of course. The power set consists of the events. So like you could have, you could get a 1 or a 2. You could get a 1, a 2, or a 3. You could get a 2, a 4, or a 6, or like you could just get a 1. And what I'm describing are subsets of the sample space, so they are elements of the power set. And then the measure function, it's probably quite clear now that M corresponds to the probability of events because I've got this P below. So probability, the way you think of probability, I don't know if you have thought about it as a function before. You know generally that probability, hope you know, probabilities are always between 0 and 1. And numbers between 0 and 1 are definitely non-negative real numbers, so it satisfies that one. It's a function from the power set of some sample space, and it's to the non-negative real numbers, and it satisfies this. And yeah, just a point that I was going to make is, with probability spaces, the probability of like the whole space of like the probability that something happens, something out of all the possible outcomes, that is 1. And now you've probably used that fact when you're kind of calculating probabilities, that people often say probabilities sum to 1. Like if you take every possible outcome and add it up, or rather add up the probabilities, you're going to get 1. And so this is why probability spaces are like a special case of measure spaces, because in measure spaces in general, we don't have to have the measure of the whole set being 1. It could be 5, it could be 27, it could be 32, it could be any number, literally any number at all, because you can, I mean, that's a bit of an aside, but you could kind of scale it up and down. Ooh, just multiply everything by the same constant. So yes, and the measure or the probability or the whole thing is 1. That's something special about probability spaces. And also, you may remember way back at the beginning, I mentioned complements, and you might have also seen this fact that the probability of a complement, which means like not A, whatever happens when A doesn't happen, the probability of that is 1 minus the probability of A. And this is using the fact that the probability of like the whole space is 1. Because it's just like at the beginning where we said the probability, we said the area of the remaining bit of the rectangle when we take away A would be the area of the rectangle minus the area of A. So this is the area or the measure or the probability of the whole thing minus the probability of A. So hopefully you're kind of seeing the links Your mind may or may not be blown. We're going to move on and do an example. Cool. So, oh, do you have to move chat again? Was my stuff in the wrong place? Cool. Chat's back. So, my example is going to be a coin toss, which is kind of a classical, very standard probability example. I'm going to show kind of how it relates to like the measure space theory. So I've got a very nice picture of a pound here to help you visualize the fact that I am tossing a coin. So the set omega is the sample space. That's like what we had on the previous slide. So now we're going to say, okay, what's the sample space when I toss a coin? You could get heads and you could get tails. That seems fair enough. So it's H and T to represent heads and tails. The power set consists of events. So what possible like events could we have? What ways could we describe the outcomes? Multiple outcomes or a single outcome. So it's kind of like we did before. What do people think are the elements of the power set? Again, you should have more of a clue this time, seeing as we already looked at power sets.
Yeah, because we did the extra bit of set theory that we weren't sure if we were going to do. We talked about power sets quite a bit. So your sample space. Let me get this right. So your sample space is the sort of overall set, and your measure on that omega thing has to be 1. So it's a bit like. So I'm still thinking about it in terms of area. So for me, the brain.
Yeah. So it's like our rectangle has area 1.
Yeah. For me, it's like probability and area don't really feel like the same sort of maths, but somehow those two branches of maths.
But they are. Mind blown.
Yeah, loads of people are doing the same thing that when we did a practice session chat, Flora got me to try and list the things in the possible event outcomes, and people are going for the same things as me. H in curly brackets is one of them, and T is one of them. I can see in chat, and I also forgot the other two.
Yes, there are more.
Which are now coming up that.
Okay, so I've revealed a bit.
Okay.
You've got H, you've got T, and if people are using the right curly brackets, then I'm very proud of you. If not, don't worry, you'll learn. When we do study set theory, it's like really important that you have curly brackets in the right places, because obviously, like the set that has H in it is not the same as H itself. So we have to have curly brackets here to show that this is like a separate event. So the event that you just get heads. This is the event that you get tails. This is not the event that you get heads and tails. It's easy to fall into that trap when you're just kind of reading it out. It's the event that you get one of these things. So when we talk about events as subsets, what we mean is your outcome will be some element of that subset. So like your outcome will be heads or tails. It'll be something that's in this set, which is hopefully always true. Which brings me on to the next point. Do people remember what else is in the power set apart from these things?
Yes. Some people in chat. Sorry, that was a question for me. Some people in chat.
Yeah, I can't see chat.
Remembered that the empty set is part of the power set. Somebody's asked why. Can we get a reminder for why the empty set?
Yeah, absolutely. So, like, why is the empty set? I'll do it on both levels. So, like, why is the empty set in a power set in general? So, the empty set is in a power set because it is a subset of the set. It's a subset of every set, because the condition for being a subset is that all of your elements are also elements of omega. So like you can see quite easily that all the elements of HT are elements of omega, because omega is the set that has H and T in it. But the empty set, this is just a kind of abstract symbol that means empty, no elements. It doesn't have any elements. So if you say all the elements are in omega, that is a true statement because there's no elements to check. It's like if I said every even number is 2 times something. You'd have to say, okay, I'll start with the first even number, I'll go with the next even number, and I'll check them all. I mean, that might not be a very good method, seeing as there's infinitely many, but that's the intuition. Whereas with the empty set, you would be like, okay, I'll check every single element of the empty set. Oh wait, there's none to check. I'm done. Proof ended. It's a subset. So that's why it's a subset of any set. That's why it's in the power set, and it's in every power set. No matter what power set you take, the empty set will always be part of it.
Actually,
and so if you're kind of struggling to see what it represents in the probability context, it actually represents nothing happens. Because if your outcome is an element of the empty set, that means you have no outcome because it has no elements.
I actually misread the question in chat, sorry. But yeah, okay.
Okay, I was going to say, I hope that answered the question, but if not, that's just an aside about the empty set.
They were confused about why the empty set hadn't appeared on the slide yet, and then it did appear while I was reading the chat message out.
Oh, okay.
My fault. Okay.
Yeah, no, that... what I was going to say was, those of you who are eagle-eyed would notice that I hadn't closed my big curly bracket, so you knew there was more to come. Like, if I go back a step, you know that this is unfinished. This is not the whole set, but I just added it on. And the only reason I had it on a separate transition is just to create a small level of suspense in case people had forgot that it was going to be there.
Okay. You've got your power set of all the subsets from your sample space.
Yes, I have.
Your job is to put a measure onto those items.
Yes, exactly. So the measure function is the probability of the events, as we recall. So hopefully everyone can agree the probability of getting heads, I should have mentioned, is a fair coin. We're kind of doing the whole modelling assumptions thing where we say there is completely equal probability of getting heads or tails, which may or may not be true depending on what coin you're using. But we're going to say probability of our outcome being in this set. So the probability of getting heads is a half. The probability of tails is a half. Hopefully that's still quite uncontroversial. And then, does anyone know what the probability of this set would be? So the one I'm kind of like under, the one which is actually the same as omega that has H and T in it. So what is the probability that your outcome is H or T? And there's more than one way to do this.
People in the chat think either 1 or 0, depending on what you think that means.
Yeah, so
I think votes
it's that tricky thing again. So if I said the probability that you get heads and tails, then everyone's like, well, no, you can't get both, Flora. That has probability 0. But I should phrase it very carefully. What I meant to say was the probability that you get heads or tails. The probability that your outcome is in the set heads, tails. So the probability that you get one of these things, either heads or tails. And so the people who said 1 were right. It is 1. There's 2 ways to think of this. So the first way is, well, this is just omega. H, the set that has H and T in it is just omega. And you told me on the previous slide that the probability of omega is always 1. The probability of the whole thing is always 1. So that's like easy. Probability is 1. The other way to think of it is, here we have already written out the probability of H by itself and the probability of T by itself. And these are, as we can see, subsets of omega, and they do not have any overlap. There are no elements that are in both of them. So when you can kind of like take the measure or the probability of the union of these two things, which means this thing and this thing together, that is going to be the probability of this plus the probability of that. So it's the good old M of A union B thing at work again.
Cool. One left. We need to decide what the probability of empty set. What?
Yes.
Well, I guess not the probability of empty set, but the probability
the probability that your outcome is in the empty set, which might help you think about it.
Yeah. So each of these is sort of works like or if you've got multiple things in that set, because we're thinking about the probability that your event is inside that particular subset, and the subsets kind of have different sizes, I suppose.
Yeah, and it's like union. If you have studied probability, you might have thought of like A union B as A or B, and that is the kind of correct thing to be thinking about. Like you've got the union of H and T, which is a set that has H and T in it, and so the probability of that is going to be these things added. I will press on and say the probability of the empty set. People are saying 0, that's good. The probability is 0, and that is because the probability that you get no outcome has to be 0. In this experiment, we're going to get some outcome. It is going to be heads or tails. You can't just not get heads or tails. Like, you have to get one of them. So the probability of that is 0. So the kind of intuition way of thinking about it is one way to get it. The other way to have got it, which is kind of weird and probably you wouldn't do this, but you could if you wanted to, is to think of the empty set as omega without omega. So like omega complement. Remember when I talked about the complement of a subset earlier on, which is like what's left when you take that subset away. So if you take omega away from omega, what have you got left? Nothing. So that's the empty set, which means that you do 1 minus 1, and that's 0.
People in chat are suggesting there was a sort of someone suggested what if the coin lands on its side, or Ali wants to know what if it disappears.
Yeah. No, when we were doing the run through, I was like, so obviously, you know, you have to get heads or tails. There's no way you can't get an outcome unless someone like steals the coin from midair and like it gets stolen or it falls off a cliff instead of falling on the ground. Like, there's all these scenarios that you could come up with, but you have to remember that when we're doing something like this, to make it kind of clear, mathematical and rigorous, we have to have like set of assumptions. And one of our assumptions is that the coin is perfectly fair and has half probability of landing on one side or the other. Another assumption is it will land on one side or the other. It's not going to spin and like land on its edge magically.
But there's nothing to stop you putting coin disappears, coin lands on side, coin falls off a cliff into your sample space.
I mean you could add extra events, absolutely. Yeah.
What if I steal it for burritos? Disaster. We've put all these things into the sample space. Chat's mad today.
We should create a sample space with everything that everyone suggested. I think that'd be quite funny. So yeah, you could have other things, but
okay, so we got some probabilities aside, and it works like
for now. I think we'll move on. So that's probability spaces. We're going to kind of take a whole side note and to talk about integration just for a moment. Because at the start I said how measure theory is an area of pure maths, and some people like to think about maths not just for the fun of it, but also for why is it useful. So measure theory is useful because it is related like closely to the theory of integration and what functions we can integrate. So this guy on the right is called Henri Lebesgue. He's French. He used measure theory to develop his theory of integration. I've just given him a red nose with the pointer. That was not deliberate. So yeah, when you kind of, if you study integration at university, you can study kind of different ways of looking at it that different people came up with. So Riemann came up with the famous integration theory, but Lebesgue came up with one which some people think is better because it allows us to like integrate more functions. So Lebesgue defined a collection of nice functions which we call measurable functions, and these are the ones like that we can measure, we can integrate them. So effectively he kind of took the step going from measuring sets, like subsets of the real numbers, he took that forward and started kind of measuring functions. Like, because when you do integrate a function, hopefully people have kind of heard of integration. The idea of integration really is like the area under a curve. I've got this picture on the right which might help you visualize it. It's like you're looking at the area between some curve, like the graph of a function, and the x-axis. And so we're measuring something. It's an area, you know. So the idea of Lebesgue's like definition of what integration is, he basically defined these simple functions, which were like these flat functions that are basically rectangles. And then he had lots of them and he took limits. And so you might have heard of something called the trapezium rule, which looks quite similar to this picture, which is basically where you're kind of approximating the integral of a function, or like the area under a curve, by doing like lots of trapeziums, lots of rectangles or whatever. But what Lebesgue did was a step further than that, because you can kind of take the limit where you have like infinitely many little rectangles. And then what you get, if you kind of take the limit, increasing the number of rectangles and getting them closer and closer to the function, what you get is actually the integral of the function. So yeah, that's a little aside on integration. It's quite kind of complicated, the actual theory, so I'm not going into it in any detail at the moment. That is like a second year maths course at Oxford Uni, so a bit much for now. So that's integration. But before the end, I really want to show you this fun example. So I've called it a crazy example. You will see why by the end. So this guy on the right is Georg Cantor, and so he contributed a lot to measure theory, but also set theory. Like, he did loads in terms of sets and like thinking about infinity. What does it mean to be finite or infinite? So that's quite cool. But today we're going to look at a particular set that he kind of like defined or came up with, which demonstrates some really kind of cool or weird properties of like what we can do with measure theory. So I'm going to start with this interval, like on the real line, number line, which is all the numbers between 0 and 1. So think of it as just like a line segment that goes between 0 and 1. And then I'm going to kind of make a point at the point where 1/3 is, the point where 2/3 is. I'm going to take out this middle bit, just like remove it. So I'm going to leave the point at 1/3 there, leave the point at 2/3 there, but everything in between, so all the real numbers between 1/3 and 2/3 are gone. So we have space. And now what we have is 2 line segments, and each of them has length 1/3. And so when we are building the Cantor set, we kind of do it in steps. So the next step is you take 1/9 and 2/9, and what we're basically doing is removing the middle third. So like you split it into 3 equal bits, you remove the middle one, and then you split the right hand one into 3 equal bits and remove the middle one. And then of course you have 4 equal bits which are smaller, and the middle third of everything is missing. Then you take the middle third out of them, and basically you keep repeating this process. And you actually repeat it infinitely many times. Now that's very hard to visualize, but to help you try and think about it, I have a GIF and I have a picture for those who like GIFs or static images. So the GIF is showing the way you take away the middle third and it's getting thinner and thinner. And the picture is also showing that in a way that you can kind of see everything at once. Sometimes this is called the Cantor's dust, because what you are left with at the end is just like a sprinkling. It's not like what we started with.
It's sort of fading away.
So,
isn't it? It feels like it's fading away to the bottom of the picture, like the printer ink's running out.
Yeah, exactly. Yeah. So the fact that it looks like it's fading away into dust is going to make the next bit kind of more surprising. What I'm going to ask is, once we've done this infinitely many times, how many points are left? How many points do you think are left? Take a wild guess. It doesn't matter if you get this wrong because it's quite unintuitive.
We've done a lot of chopping, and it looks like it's kind of
taking away a lot of points.
People in chat are comparing this to Sierpinski triangle, but I feel like it's more like the Menger sponge if you're going to compare it to a fractal. But yeah, these things are all quite some similar ideas. Alfie thinks there's maybe at least 1 point left inside the set, which I think is...
Yeah, there is at least 1 point left, and that is the good thing to think. If for no other reason, the reason to think there's at least 1 point is because I've already defined the empty set. There's only one empty set because it has no elements. And if the Cantor set was going to be the empty set, then it would be a bit of a boring example.
Yeah, if the Cantor set was the empty set,
we could just say that.
Don't get to put your name on it, do you?
No, if he just come up with another way of getting the empty set, I think everyone would be like, well, yeah, it has no elements. So yeah, it does have elements.
Possibly infinitely many points left over.
Someone said that.
People are saying, so Molly and Dirichlet, and let's have a quick replay.
Great.
Anonymous person I saw, and another anonymous person.
Good. We love an anonymous person.
Maybe not guessed that there are infinitely many points left over.
Yes, so that's the truth. Well, they might know, maybe they've seen it before. So if you have seen it before, keep quiet about the next bit. So there are infinitely many points left over, because if you kind of, it's like, what do you mean there's barely anything left over? If you think about it, the point at 1/3 is always going to stay there because we take away the space between 1/3 and 2/3, but the point at 1/3 and the point at 2/3 is never going to get removed. We're only taking things from like the middle bit in between them, and then the middle bit in between those middle bits, and so on and so on. But you're never going to take away the point 1/3. You're never going to take away the point 2/3 either. And actually, there's lots of these points that you're never going to take away, like the point at 1/9, the point at 1/27th. And people might be thinking, I'm noticing a bit of a pattern here with all the numbers that she just said. And you would be right to notice that. And there is a lot more to say about the Cantor set. If you want to go home and research it, I mean, you are home. go away and research it afterwards, then like that's a great idea. But for now, I'm going to move on to another question, which is about the Cantor set still. What is the length of what is left? So I don't expect you to answer this straight away. We're going to do it in steps. The way we're going to think about it is, hopefully we can all agree, the length that we started with is 1. I mean, I've taken the numbers away, but if you remember, I defined this as the line segment from 0 to 1. All the real numbers between 0 and 1. So the length of the segment to 0 to 1 is just 1, right? So we started with 1, and then we obviously remove bits. So let's think of it step by step. What do we remove? So we remove 1 times 1/3 at the first step. Seems reasonable. Just that's the length of 1/3. And then we remove 2 times 1/9, because that's a 9th, because it's 1/3 of 1/3. And if you remember, 1/3 of 1/3 means 1/3 times 1/3. And we had 2 of them. And then what do people think the next one might be?
Chat lag.
Hopefully someone guesses this.
Chat lag. And I'm trying to keep up. I'm trying to talk to people in chat as well about other stuff that they're saying that's not quite.
No, it's fine. I know there is a lag. Just like have a calm 20 seconds while we wait for everyone.
Either 3 or 4 times 1/27. Some expressions are coming in with ends in.
Oh, very exciting, very exciting. So yes, the next step would be 4 times 1/27. And you can kind of look at the diagram. So like 1, 2, 3, 4, and then this is the point like 1/27. So these are like 27ths of the interval. And so since people have already started coming up with expressions with ends, I will do a reveal that the general, I mean, you can still just keep guessing if you want to, the general term is going to be some power of 2 times 1/, some power of 3. Hopefully everyone can kind of see that's the progression that we've got going. But this is 2 to the power of 1. This is 3 to the power of 2. So everyone's thinking, okay, it's not going to be like the same thing. If I reveal what it is, it's 2 to the n minus 1 times 1/3 to the n. Because we start with n is 1, 1 minus 1 is 0, 2 to the 0 is 1. So that gives us the 1 times 1/3, and then we get 2 times 1/9, and so on and so on. So if you think about what do we remove in total, when we take infinitely many steps, like we remove this at each step for n is 1, n is 2, n is 3, and so on, up to infinity. So in total, we're going to have an infinite sum. Now this is quite exciting. You may or may not have studied sequences and series and stuff like that yet, so don't worry if not, because I'll just show you a fun fact and guide you through it. So we are summing, this symbol means summing, from n is 1 to n is infinity, 2 to the n minus 1 over 3 to the n. So we're adding all of them up. And so you might be thinking, how on earth are we going to evaluate that sum? Like, how do we know what the answer is? But luckily, this is actually a geometric progression or a geometric series. If you've heard that term, it means that we have a first term, and then to get the second term, we multiply by some number, and then to get the third term, we multiply by the same number, and we keep multiplying by the same number to get every subsequent term. So here, hopefully you can see that you multiply by 2/3 each time, because you have 1/3, and then you have 2/9, so you multiply the top by 2 and the bottom by 3. And we have a formula which deals with geometric series. This gives us the answer when we're trying to sum one up. So if you haven't seen the formula, don't worry about it. It is, I think, on the A-level syllabus. Basically, it's the first term divided by 1 minus the common ratio. So we're going to use this formula. So if anyone remembers what the first term is, that was 1/3. Does anyone remember what the common ratio is? I kind of just gave it away just now.
It's 2/3, right? Because each one
multiplies
by 2 on the top and 3 on the bottom.
Yeah, so we know that this is equal to 1/3 over 1 minus 2/3. And now hopefully everyone can do 1 minus 2/3. You know that that's 1/3. So we get 1/3 over 1/3. Now what's that, everyone? That's 1. Hopefully everyone knows that's 1. So taking it back a step, we said we started with length 1, then we removed something. What we removed added up to 1. So what length are we left with? It's 1 minus 1. And that's 0.
1 minus 1 is 0. Welcome to the Oxford Online Maths Club.
This is the point where you're obligated to say that. Welcome to Oxford Online Maths Club. 1 minus 1.
There's another method in chat. Can I tell you the other method in chat?
Yeah, of course you can.
This approach that Floris has done is to add up all of the bits that were getting removed. So look at that first chunk that gets removed, 1/3, and then the next couple of chunks that get removed, and add up all of the stuff that gets removed. There's an alternative approach in chat to think about what happens to the length of the black line in terms of a fraction each time. That when you chop out the middle third, you're left with 2/3 of the shape each time. So it's sort of like a sequence of 2/3. Somebody put 2/3 to the power of infinity.
Thinking about what's left.
Which gives the same answer.
Because if you do 2/3 to the power of n, and then you take n really, really big, you're getting smaller and smaller because you're taking 2/3 of 2/3 of 2/3. So that gets a much smaller fraction, and then it will tend towards 0. Yeah, that's a great way of thinking of it. But yeah, they're just two alternative methods of getting the same thing.
Yeah, I like it.
So that's great. So the kind of crazy, surprising thing about the Cantor set is it has infinitely many points, but length 0. And you can build it just by iterating these steps. And it's like, wow, infinitely many points, but length 0. That's nice. I think it's cool.
Infinitely many points, but they're all sort of quite separate from each other.
They are separate.
The measure doesn't quite add up to being anything more than 0.
Yeah, and when something has measure 0 or length 0, what we call it in measure theory is a null set. You might have heard the word null to mean nothing. So it's a null set because it has 0 length or 0 measure, but it can have infinitely many points. And this is, I think, one of my final slides, but I've just put a little tiny word here. For anyone that knows anything about countable or uncountable sets, that's a really fun area of set theory. It actually has uncountably infinitely many points. What that basically means is that it has the same kind of infinity as the real numbers rather than the same kind of infinity as the integers.
Types of infinity. I don't think we've done types of infinity on the live stream yet.
No.
One day.
I was going to say, one day we should have a set theory one and talk about lots of infinities. But yeah, if you think about how the integers are spaced out, there's big gaps between them. They are just dots on a line, and then the real numbers, there is the whole line, and every possible point, every single thing on that line is included. You can kind of see that those are different kinds of infinite set, maybe, if you visualize it. So this actually has uncountably infinitely many, so that's like the real numbers. It's not like the integers, but it still has 0 length. So it's quite impressive that you can find a set like that, just using some simple kind of measure theory.
Nice.
Yes, which brings me on to the last slide. So if anyone found measure theory a bit too much or a bit too abstract, then I apologise to you, and I've put this nice little drawing here. Credit to Math with Bad Drawings, I did not draw this. It's explaining abstractitude sickness, the disorientation and nausea of ascending to a new level of abstraction when studying maths. I've also included some memes. The bottom one is my own, the top one is not my own. interested. So yeah, hopefully that's kind of given you an idea of what measure theory might be about and how it links to probability, it links to integration, it links to set theory, and it kind of brings some quite different areas of math together.
Thank you very much. And you've reminded me that chat has reminded me that we talked about accountability. It was an episode with just me as well, I've remembered, back in season 2, episode 10. Thank you, anonymous people in chat who can remember better than me what I've previously
Well, it's nice that they remember. It must have been memorable.
Better than me. And there's already questions about, now that we've mentioned infinity, there's questions about infinity going on in chat that I think need to be deferred to a course on measure theory. There are questions about infinite unions, there are questions about infinite intersections but only countable unions, which doesn't make any sense if you don't know what countability is. But measure theory has issues to do with how big is your infinity. The Cantor set's got infinitely many points in, but it's still got measure 0. So it's kind of small, even though it's got infinitely many sets.
Small even though it's infinite.
Measure theory
but people raise good points about kind of infinite intersections and unions. That does come up and is quite important in measure theory. I've kind of brushed over that. But yeah, it is a thing that is important in measure theory.
Cool, okay. Link in further reading to a previous episode that I've completely forgotten about, where I talk about counting. Thank you very much, Flora, for coming on the live stream and showing us stuff about measure theory, probability, geometry, areas, integration, and everything else. Always a pleasure. Anything else that we should say before we wrap up?
I don't think so. I hope everyone enjoyed it.
I hope you have a nice rest of your evening, everyone. If your day was a 1-star or 2-star day, I hope it's now up to 2 or 3 maybe. I'm not going to run the poll again, just in case. Take care, have a nice evening, and we'll see you again next week for another episode of the Oxford Online Maths Club. Bye.
Bye.